The words that I like to use for the product rule is I say the derivative of the first times the second plus the first times the derivative of the second. Or the derivative of f times g plus f times the derivative of g. You've got to find a way that makes you do that thing. You've got to find the words that are going to make you remember this pattern. Notice, the good news is, we can notice is that this is made up of multiplication and addition, so we can kind of remix it to make it work for us. That's the good news. The bad news is, it's made up of multiplication and addition, so we can kind of remix it to make it work for us. So that's good because you could find something that works. That's bad because now you have to find something that works. We all think we want to have choices until we have to make choices. So this is the words that I was programmed with. I mean, I was taught when I learned this. The derivative of the first times the second plus the first times the derivative of the second. The derivative of the first times the second plus the first times the derivative of the second. Then all we have to do is remember those words when we go to implement the problem. So let's practice. For example, we're going to make a product of functions. Let's say that y is equal to x cubed times sine of 5x. Here we have a product of functions. One of the functions is x cubed, the other function is sine of 5x. So since we're trying to find the derivative of a product, we'll use the product rule. So f is x cubed. I need the derivative of f. That's one of the pieces that I need. So I'm going to just write underneath f prime is 3x squared. There's the derivative of the first. And if g is sine of 5x, then g prime, or the derivative of the second, will be the derivative of sine of something is cosine of that thing times the derivative of that thing. We had to use the chain rule because it wasn't just sine of x, it was sine of 5x. It wasn't an extensive chain rule that we had to use, but there was a chain rule that we had to use because the chain rule is always in effect. Now I've got all the parts. So dy dx is the derivative of the first times the second. Plus the first times the derivative of the second. We wouldn't want to write it this way, but by writing this down, we can see very clearly what parts we put together. We wrote down all the parts that we're going to use, and here we are visualizing the parts put together. This is not good syntax for a final answer. Specifically, I don't like this. X cubed times 5 times cos. That's a terrible order of things. At this point in your mathematical career, you should look at this x cubed times 5 cosine of 5x and go, ugh, that looks terrible. If you're not like, oh, ugh, that looks terrible, you need to look at more functions. And this needs to be aesthetically displeasing to you. So this should evoke some kind of like, ugh, it doesn't look right. I mean, it looks correct arithmetically, but it doesn't look right. You feel like, oh, no. This is 3x squared sine of 5x. Thank you, first term from product rule, for coming out in a nice order. But now I've got to remix this. I spelled plus wrong. The lines cross each other. 5x cubed times cosine of 5x. And you go, oh, that looks better. Doesn't that look better? Does that second one look better? The answer is yes, it does. So just say yes. And then make that true. I'm not saying what you have to think. I'm just like saying what you have to think. Just kidding. But if you write your constants like in the middle of your term like that, I mean, people are going to think you're weird. Maybe that's what you're going for. I don't know. You don't want to be like all those Brittany and Justin wannabes. I'm going to write my constants in the middle. I'm going to put them first. The whole trick with this process is a reading exercise. So the question is going to come up, how will I know when I'm using the chain rule and when I'm using the product rule? And the answer is, do some more problems until you stop asking that question. The answer is, you'll just know. You just have to build an instinct for it by doing a lot of problems. And sometimes, this is the hard part, getting those problems wrong. Reading things wrong. So like we saw yesterday, this problem is not a product rule problem. 5 is a constant function. Sine is nothing by itself. This is sine of x cubed. So we're just going to do a chain rule, right? So dy dx, this is just chain rule. Derivative of 5 times the sine of something is 5 times the cosine of that thing times the derivative of that thing. At which point you'd be like, oh, ew, gross. Just like the chain rule is always in effect, the product rule is always in effect as well. Now, we don't need to use the product rule on this problem, but we can view it as a product. As long as we read the sine of x cubed, that is one thing. We can't just say sine and then like have x cubed be its separate thing. Those things are not being multiplied. But we can just say that 5 is a function of itself, is a function by itself. If we read it that way, that first term isn't going to be anywhere, is going to be 0. If f is 5 and g is sine of x cubed, then f prime is 0. And that's why we don't need to invoke the product rule for this particular function. Because that first term of the product rule, if we make one of the functions 5 a constant, the derivative of that constant is 0, and that wipes out one of the terms. So when I write f prime g, I have 0 times sine of x cubed. I would write 0 times sine of x cubed plus 5 times 3x squared cosine x cubed. Which means secretly, when we say we're just going to go straight to the chain rule, just do the chain rule, And secretly, we're doing the product rule. It's just that one of the terms was 0. So the big villain reveal. Aha! It was the product rule the whole time. Ha 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 ha. The reason that I point that out is that we want everything to be nice and consistent. We have to, the words have to mean something. It's not like we're just like writing prose in English. We are writing math stuff. Math requires a precise language. Any questions? Now here I've got 5 times sine of x cubed, but if I had 5x times sine of x cubed, now it's product rule. How's everybody okay? Everybody looks stoked about this product rule. You don't have to memorize it, you just have to remember it. Okay. At this point, all you need to do is build strength. You have the proper form. All we need to do is build strength and persistence. It's a reading exercise. What's the overarching rule in this problem? Product or chain? Those are the only 2 choices we have. What's like the primary rule that we're going to hit this with first? Product rule. What are the 2 factors? What's our first factor? 5e to the 2x. What's our second factor? Tangent cubed of 4x. What are we going to have to do when we take the derivatives of each of those terms? What are we going to have to use there? What do we always have to use? Chain rule. We're going to have to use the chain rule on both of those derivatives, but that's just part of the derivative taking business. So let's separate it out into our parts. Our first function is 5e to the 2x, and our second function is tangent cubed of 4x. Remember, we're reading tangent cubed as the cube of the tangent of 4x. Tangent cube is a short notation for the cube of the tangent. The derivative of 5e to the 2x is 5 times e to the 2x times 2, or just 10 e to the 2x. We're already trying to grow past the part where we need to write down all the different steps. We just know what's going to happen. The point of doing math class, the point of doing a math class is to not have to do all the math all the time, to not write down every step. G prime. This one is going to get messy because I've got a couple of chain rules going on. I've got the cube of the tangent of 4x. See how many times I said of? Cube of tangent of 4x. And there's going to be a couple chain rules show up. The derivative of something cubed is 3 times that thing squared. Times the derivative of that thing. The derivative of tangent of, there's another chain rule showing up. The derivative of tangent of 4x, the derivative of tangent of stuff is secant squared of that stuff times the derivative of that stuff. The derivative of 4x is 4. So if we read that as the cube of the tangent of 4x, it tells us that the chain rule is going to show up twice. Because we said of. Now we can put things together. Using the product rule, I take the derivative of the first. I write the derivative of the first times the second. Plus the first times the derivative of the second. I'm going to take the 3 and a 4 and put them together. So 12 tangent squared of 4x times secant squared of 4x. And then I've got that 5 times 12. So I go, oh man, I wish I would have seen that coming. Because now I got to write this whole thing over again. And be like, all 10 e to the 2x tangent cubed of 4x. Thank you, first term, for once again being in the nice order. And then 5 times 12 is 60 e to the 2x times tangent squared of 4x times secant squared of 4x. And this we might consider acceptable. This is where I would expect your cleanup to go. Clean up each individual term by combining your coefficients or any constant coefficients and writing your other factors in a nice proper order. Exponential followed by your trig function. I'm not really a fan of tangent squared going in front of the secant squared, but it's fine. It's fine. That's how they showed up here, naturally. So we'll just go. Now, when you go to check the answer online and a computer does the problem, the computer might be like, oh, let me try to clean that up for you. And notice that there's a common factor of a 10. There's a common factor of an e to the 2x, and there's actually a common factor of tangent squared. So you might see something with all this factored out, leaving just a tangent of 4x plus 6 secant squared 4x. So the good news is there's a lot of ways that we could end up writing our final derivative. The bad news is there's a lot of ways we can end up writing our final derivative. Whether or not we recognize that is a function of our algebra skills. As far as the aesthetics of these two, for me, these two are pretty much the same. They're both kind of equally aesthetically pleasing. And it also kind of depends on what other stuff I'm going to have to do. Right now, if I was going to stop at first derivative, I'd probably just leave it at this one. Because I've already written this whole thing over again just to put the 5 and the 12. And that's just because I don't have an eraser where I can just erase the 5 and the 12 and write 60 where the 5 is. If I had left some more space after the 5, I could have just changed the 5 into a 6 and shoved the 0 in there. And then scratched out the 12. But I'd be like, oh, well, I only need the first derivative, so I'm just going to do this. Now, if the problem had been set up, it's like, well, okay, now find the second derivative, which we haven't talked about, but you can probably guess what we would do. Second derivative is just the first derivative of the first derivative. That means take a derivative again. If I leave it in this form, I've got to do the product rule like twice, because I got to do a product rule here. And this is a product of 3 things. So I'm going to have to do like the super product rule. I didn't tell you what it is because I like to surprise you with that, but there's a derivative of f times g times h. But down here, I got the derivative of the first is the product rule times the second plus the first times the derivative of the second. So it would slightly reduce the number of product rule that I have to do. At that point, you're just down to what your favorite is. Any questions? That, by the way, is the entirety of my discussion of the second derivative before I assign homework on the second derivative. 51. I'll make you guess at what it is. How's everybody okay? All this is now is just stacking up functions that we're familiar with and then learning more functions. So in the previous problem, the primary rule, the first thing that we come across, we looked at that function as, we looked at our function as a product. I said, I'm going to use the product rule because I see a product right here. What do you see here? How have I changed this by dropping that previous function into a radical? We could do a chain, right? We could just say the derivative of the square root of all this junk is 1/2 of all this junk to the negative 1/2 power times the derivative of this stuff. That would be a really convenient way to do that because the derivative of the inside is like sitting right here, right? So reading this as a chain rule is going to be pretty convenient to us because we'll just be able to do 1/2 this stuff and then we already have the derivative of the inside. So we could read this as a chain rule, and then the derivative of the inside is the product rule that we had from before. Is this the only thing that we could have done? Clearly not, because I just said, is this the only thing we could have done? We could have also broken this into a product rule because this is just an exponent being applied to a product, and exponents distribute over products. So if you wanted to be different, not be one of those Brittany and Justin wannabes. I don't know if anybody watches South Park anymore. We could also read this as a product rule. In this case, the derivative of the first times the second is going to be some chain rule. But when you have something like a square root of tangent cube, the square root of the cube of tangent of 4x, you could read that as the 3/2 power of tangent of 4x, and just do 3/2 tangent the 1/2. That would be a different read to open up the problem. Any questions? The best one to do first is whatever it occurs to you to do first. Whatever your instincts tell you to do first, that's the one you go with. You might be different than the person that you're working with. And you're just gonna have to get over that. It's like doing stuff in Windows. There's like a lot of different ways to do a thing. And your way is obviously the best, and people that don't do it that way are clearly wrong. You know what I mean? Like keyboard shortcuts. If you're using keyboard shortcuts, you are correct. If you click on menus, then I don't know what's wrong with you. No, I just click on this menu and then I roll down to here. It's like a damn sociopath. It's just weird. What the hell's wrong with you? Now, if I don't want you to use the product rule on this, right now you're thinking, this is the same as the last one. And now you say, oh, now you suck. Now, Leach, you're being a dick. Because now the exponent does not distribute, because this is an exponent over sum. Exponents do not distribute over sums. Chain rule for you. So I'd have to do 1/2 of all that junk to the -1/2 times the derivative of that junk, which is actually the same as the previous one. So there's not a lot of extra work going on here, but we cannot read this as a product rule because of that plus. That plus just messes everything up. Because exponents do not distribute over sums. Any questions? How's everybody okay? This last thing is exponents do not distribute over sum. This is kind of an important thing that we don't always think about. We think about our distributive property, and because the distributive property is always only presented with parentheses and always just with multiplication, written as juxtaposition, we start throwing parentheses out by just distributing things that aren't multiplication. And one of the artifacts of that is exponents do not distribute over sums. Like x plus y squared is not just x squared plus y squared. That's what I mean when I say exponents do not distribute over sums. The square of a sum is not the sum of the squares. We have to x plus y squared. There is an x squared and there is a y squared, but there's also a 2xy along with the y squared. The reason for this is not weird arcane algebra rules. The reason for this is that's how numbers work. We didn't do this. The numbers did this to us. Because of the way that we describe numbers, they decide how the rules of algebra work, right? (23) squared is not just the 400 plus 9. We're missing 120 there. Right? Yeah. We're missing that 2xy. So the x plus y squared thing is, that's just how numbers behave. The plus 2xy is there because that's how numbers behave. Nothing fancy going on. That's what numbers do. So that's why we do it. Nothing fancy going on. We're just following the rules that the numbers laid out for us. Any questions? How's everybody okay? That's just me trying to find out if I can make anybody write LOL nice planning in your notes. Well, some people do that. I don't know if I need to write that. How's everybody okay? All right, so we have a new rule called the product rule. The product rule in words that I use is the derivative of the first times the second plus the first times the derivative of the second. That's my mnemonic for product rule. You might be like all f prime g plus f g prime. That might be one you use. Some people are like all f prime g plus g prime f. I like to call those people criminally insane because what the hell? I'm just kidding. If that works for you, then you should do that. It's all the same stuff, right? Because it's multiplication. So it's f prime g plus f g prime. F prime g plus g prime f. And that one makes me, I really hate writing that one. But if that's what works for you, then that's what you need. That's how you're going to implement the product rule. Is everybody okay? We have a product rule and we also have a quotient rule. Because we have the chain rule, we don't really need the quotient rule. So the quotient rule is always like kind of like hanging on. It's like, well, hey man, I'm cool too. And the product rule and chain rule is like, oh yeah, we don't really need this guy, but you know, let's throw him a couple problems just to keep him around. So there is a quotient rule. I can't believe the disrespect I'm about to show the quotient rule. I'm just gonna like write it one time down here. I'm not even gonna write down quotient rule. I'm just gonna shove it into this bottom part. It's gonna be f prime g minus f g prime over g squared. F prime g minus f g prime over g squared. This is the quotient rule. You can get this from the product rule by writing f times g to the -1. That's why the g squared shows up in the bottom, because we're reading it as a g to the -1. So the derivative is -1 times g to the -2. But this is the quotient rule. You got a function set up as a quotient. This one is handy. Any questions? Comments? Snide remarks? At least write the name. Otherwise, it becomes like a whole villain origin story. Quotient rule shows up my office. You were disrespectful. Battle ensues. How's everybody okay? Introducing new stuff on a Friday. Jerk move. Jerk move. And I go, dude, I was not planning on doing anything over the weekend. So I don't know what you think you're accomplishing by doing it. It doesn't matter. Because now it'll be sitting in your subconscious. I like hope that you don't even do any product rule over the weekend. Just let it sit in your subconscious. And then on Monday, you'll be surprised when you remember shit. Your subconscious will be surprised, motherfucker. I remember that. All right, that's going to do it for today. That's going to do it for this week. I will see you all on Monday. Everybody have a good weekend. and thanks for playing.